Gravity is a lie, and the universe is running out of time. Before atoms, before light, just pressure and noise. In that roar, something dense and wrong condensed, seeds with their own clocks. If their fuse runs out, the rules we live by don't survive the blast. Gravity, chemistry, time. Here's the hook. We found the timer by accident. Starlight hiccuped. A star brightened for hours, then fell quiet, too sharp for a planet, too fast for a star. Gravity had drawn a line through it, and whatever did it was small, cold, and older than galaxies. Who planted the seeds? How fast does the fuse burn? And what happens when it hits zero? Let's rewind to the first whisper. The impossible whisper in the data. It started with a blip that looked like static. A distant star brightened for hours, then fell quiet, too sharp for a planet, too fast for a star. Gravitational microlensing, sure, but the timescale was wrong. The lens was compact, dense, and no bigger than Earth. The team tagged it rogue. Then another blip arrived with the same quick heartbeat. Then another. Rooms went quiet. If real, something ancient and small was bending starlight from the shadows. If those lenses weren't stars, weren't planets, and weren't dust, we'd stumbled into a population the universe wasn't supposed to have. Objects formed before stars existed. Months of surveys stitched bland sky into signal. On spreadsheets, blips formed a pattern that narrowed the mass guess: Earth mass, lunar mass, some lighter, too cold to glow, too dark to see, and showing up where models said they shouldn't, sprinkled through the halo like iron filings no magnet could lift. A human beat cut through the math. A postdoc at 2 a.m. matched a cluster of short events to a distribution curve she'd meant to delete. She didn't. She emailed. Either a software ghost or something we're not ready for. The reply: coffee. Stakes escalated. If these were planetary mass black holes, primordial black holes, then dark matter might not be a particle we could trap underground. The true dark might be collapsed knots from the first fraction of a second, hiding behind gravity alone. Action followed, cross-checks with other fields, false positive simulations, a census of free-floating planets and brown dwarfs eliminated case by case. Another group flagged Earth mass lenses with no infrared counterparts, no heat, no light, no motion you'd expect from a kicked-out planet. If they were planets, they were the strangest ever cataloged. If not, they were something else. Constraints woke up. The cosmic microwave background doesn't like too many small black holes. Gamma ray backgrounds don't like late evaporators. Lensing surveys crush certain mass ranges. Too big, ruled out. Too small, long evaporated. Yet a narrow alley remained, a slim mass window where the numbers didn't scream impossible. Seminars changed tone. Primordial black holes slid back onto slides, not loudly, not with glee, in whispers. Because if they're real, they're survivors older than galaxies and chemistry. Showing up where models said no wasn't a deal breaker, it was a dare. A microlensing campaign logged a curious trio, near-identical durations months apart toward a thin stellar field. Coincidence, probably, but it itched. Maybe patterns hid not in single events but in their distribution across masses and locations. One detail stuck. Some durations clustered near scales tied to early universe phase transitions. Nobody claimed discovery. They pinned it to the corkboard labeled weird. Curiosity turned to pursuit. An observer traded weekends for a dark control room. A theorist dusted off a calculation about density spikes during inflation. We only need a few to survive. A data scientist wrote a filter that tossed anything warm. What remained were cold signatures with hard gravitational edges. Reactions had mass. A die-hard particle physicist closed her office door. If this holds, our map of the universe changes overnight. Another drew a timeline starting with temperature and pressure, funneling to tiny collapses. Make them early and they last, if they're big enough. Impact rippled. Grants added PBH lensing as a line item. Observatories coordinated cadences to catch shorter events. A radio array listened for anything. Silence counts. A sharper beat emerged. No light, no heat, just gravity drawing a line through a star. Then the troubling thought. These objects wouldn't be inert, they leak. All black holes do. Slowly for big ones, suicidally fast for tiny ones. If the universe is studded with ancient, small black holes, each carries a fuse, we just don't know how long is left. The meeting ended. The ticking didn't. To test the whisper, we went darker. The models were unfriendly, the sky indifferent. Still, the hints aligned, too sharp, too frequent, too cold. And that distribution detail, the banding near early universe energy scales, refused to leave the board. For now, the whisper had a name, spoken out loud only in closed rooms: primordial black holes. What nobody saw coming about dark matter. To understand why the whisper hit a nerve, we need the missing particle problem. For 40 years, detectors buried under mountains waited for a tap from a weakly interacting massive particle. Nothing. Colliders cranked up the energy, hunted for supersymmetry's promised zoo. Nothing. Astronomers mapped galaxies, measured rotation curves, traced lensing arcs around clusters. Dark matter was there gravitationally, but the particle never shook our hand. The default idea, it's a new particle we haven't seen yet, started to sound like hope dressed as physics. Here's the twist. If the dark is made of objects, not particles, the rules change. Primordial black holes don't care about cross-sections or scattering rates. They don't glow, they don't bump. They're lumps of gravity that formed before chemistry had a name. That's why the stakes were high. If PBHs fill even part of the dark matter budget, decades of lab strategy shift overnight from shielding photomultipliers to watching the sky for gravity's fingerprints. But first, the walls. Constraints came from every era of the universe. Start with the hot baby picture, the cosmic microwave background. Too many small black holes accreting in the first few 100,000 years would heat and ionize the gas differently, smearing the CMB's delicate patterns. Analyses turned that intuition into limits. Whole swaths of mass get crossed out. Then come the gamma-ray backgrounds. Black holes lighter than about 1 billion tons would have evaporated by now, flooding space with high-energy photons. We don't see that flood at the expected level, so that mass range shrinks too. Lensing surveys add more scissors. If you populate halos with compact objects in certain masses, they overlens stars in nearby galaxies. We would have seen far more microlensing events than we do. Cut, cut, cut. What nobody expected was what survived the cutting. A narrow band, a slip of possibility, where PBHs could hide without tripping alarms. Roughly asteroid to lunar mass, about 1017 to 1023 grams, give or take, depending on how extended the mass distribution is. It isn't clean, it's messy with caveats, but it's there. And then the weird alignment, the microlensing blips from Chapter 1, the ones with short, sharp durations live right where the constraints are thinnest. Not proof, but an invitation. Meanwhile, a different battlefield lit up. Black hole mergers in gravitational waves. LIGO Virgo started hearing thumps from heavy binaries. Early detections included systems around a few tens of solar masses, and later the exceptionally heavy GW 190521, with component masses in the ~6585 solar mass range, sparking a thought. What if some of these were primordial? That window's far away from the asteroid mass lenses, but it matters because it showed the community something. Even compact object demographics can mislead you if you assume only stellar origins. If PBHs exist in multiple bands, the universe could be more patchwork than we imagined, seeds at different scales, forged by different early universe processes. A team working the quiet end of the mass spectrum made a careful claim. Their lensing candidates clustered near lunar mass and showed no infrared glow, no proper motion consistent with kicked-out planets. They weren't pounding the table. They were building a case where the nulls spoke louder than the detections. The key was synthesis. You don't get to say PBHs are the dark matter by pointing at one plot. You layer CMB limits, gamma constraints, dynamical heating of star clusters, microlensing rates, and you see what remains when everything else is peeled away. Then something subtle entered the conversation: extended mass functions. The universe probably didn't make all PBHs the same size. If the spectrum is broad, a model can dodge a lensing constraint here while threading a gamma constraint there. It sounds like tuning, and it is. But tuning isn't a crime if the physics motivates it. Inflationary models with bumps in the power spectrum, phase transitions with softening sound speeds, these mechanisms naturally pick out scales. That's where the banding from the data itch connects. If early universe physics imprints preferred masses, clustering and event duration stops being suspicious and starts being a prediction. Of course, there's the evaporation clock. Anything much smaller than a mountain mass would be gone today, so if you see contemporary lenses at subasteroid masses, either they're not black holes or you've discovered something radical. The allowed band sits safely above that evaporation cliff, which is why it became everyone's favorite narrow alley. Heavy enough to survive, light enough to evade accretion and lensing dragnets. The human moment arrived in a lab basement, fluorescent lights humming. A graduate student spread out printouts of constraint curves like contour maps of a hostile country. She drew a finger along the safe valley and said, "If we're going to find them, this is where they live." Her advisor nodded and added, "And if they live there, we need surveys with faster cadence and better baselines." 2 months later, a proposal landed to reconfigure a telescope's observing schedule, not to catch supernovae, but to trap hour-long blinks with surgical precision. Impact came quickly. Dark matter conferences set aside plenaries for compact dark candidates without snickering. Particle detectors didn't shut down. They pivoted to complementary roles, probing models that predict both PBHs and light relics. Meanwhile, theorists ran Monte Carlo forests, generating PBH populations under different early universe assumptions to see which ones sneak through the constraint maze, especially in the 10-17-10-23 gram window, and still make up a meaningful fraction of dark matter. What nobody saw coming wasn't PBHs themselves. They've haunted papers since the 1970s. It was the way the failure to find a particle opened a door people were tired of knocking on. The silence from underground labs didn't prove PBHs, but it made their whisper audible. And it set up the next urgency. If the dark is made of tiny horizons, every one of them leaks. That turns dark matter from a missing particle into a universe full of clocks. To hear the ticking and what it means, you have to follow the leak, Hawking radiation. The fuse, Hawking radiation as a clock. Here S where the whisper turns into a ticking sound you can't unhear. If those compact lenses are primordial black holes, they aren't inert. They're leaking. Not like a cracked pipe, more like a faint, relentless hiss from the edge of space-time. Stephen Hawking showed that when you mix gravity, quantum fields, and a horizon, you don't get silence. You get a temperature and a clock. Stakes first. Big black holes are cold. Small black holes are hot. That simple flip has teeth. It means every black hole, no matter how old or quiet, is a timer. The smaller it is, the faster the digits fall. If the dark is full of small ones, then the universe is full of clocks we never set and can't stop. To understand the clock face, you need one relationship. Temperature is inversely proportional to mass. Double the mass, halve the temperature. Shrink the mass and the temperature rises. Radiation steals energy. Energy is mass. The hole loses mass, gets hotter, radiates more, loses mass faster. That curve is the fuse. Mass up, time up. Mass down, time screams. Action, people who live in equations translate this into lifetimes. A primordial black hole with the mass of a mountain, call it 10-15 grams, lasts roughly the age of the universe. A bit heavier and it will outlive galaxies. A bit lighter and it's already gone, having evaporated in a fierce finale long before stars ever formed. That's why the mass window in Chapter 2 mattered. Survive today and you're heavy enough to still be here. Fall below that threshold and you die young with a flash. Microstories make it real. A pebble-mass black hole, ridiculously tiny by astrophysical standards, would be gone before you blink. Less than a trillionth of a second and it would vaporize, unloading its stored energy in a spray of particles. A mountain mass one is different, colder, patient, lingering across cosmic eras like a coal that refuses to go out. Same physics, different pace. Meanwhile, the spectrum of what comes out shifts with time. Early on, when the whole is heavier, it emits mostly low-energy photons and a trickle of light particles. As mass drops and temperature rises, higher-energy quanta join the party: electrons, muons, eventually quarks and gluons that hadronize into jets. The closer you get to the end, the harder and brighter the spectrum. The fuse doesn't burn evenly, it flares at the end. Complication: we're still playing a semi-classical game. We use quantum fields on a smooth space-time background to get the radiation. That's good enough until it is. Near the final moments, when the whole shrinks to scales where quantum gravity should speak, our math stutters. Do you get a runaway fireball, a burst of gamma rays with characteristic structure, a Planck mass relic left behind? Each answer writes a different ending on the universe's ledger. This is theory space, credible possibilities, not settled facts. Impact: once you accept Hawking's clock, PBHs become more than dark matter candidates. They're time-stamped artifacts. Find one in the right mass range and you can predict, not perfectly but meaningfully, how much time is left on its fuse. The late-stage surge isn't just fireworks, it's agency. It can heat, ionize, seed particle cascades, and this is the part we'll come back to: dump concentrated energy into a small region of space at energies our universe rarely accesses anymore. What nobody knew at the time the idea first landed was how human that clock would feel. In a late-night meeting, someone asked, if there's one within a few hundred light years that's small enough to pop in the next million years, would we know? The room paused. The honest answer: probably not until the last seconds, unless we're watching hard in the right band. The hiss is subtle. The final breath is not. There's a quiet irony here. The very constraints that carve out the allowed mass window also define the tempo. Too light, and PBHs would have shouted in gamma rays long ago. Too heavy, and they're essentially eternal, cold, and silent on human timescales. The band that survives is the band where the fuse is long but not infinite, the radiation faint but not absent, the finale distant but guaranteed, given enough time. Meanwhile, there's another thread tied to the clock: information. If evaporation is real and complete, what happens to the information about what fell in? The page time, the moment when half the information has effectively come back out in correlations, arrives earlier for smaller black holes. That means small PBHs cross the line where the emitted radiation carries structured entanglement relatively quickly. The hiss isn't pure noise anymore. It could be tangled with the hole's interior state in ways we're still trying to decode. Here is where the stakes sharpen. Late evaporation couples the interior's deepest secrets to the outgoing quanta. If anything about the black hole's birth environment or internal microstate can imprint on that radiation, the end stage isn't just an energy event, it's a message event. If there's any message to read. That's a big if. And we'll handle it when we get to horizons as switchboards. For now, keep the clock in mind. Human moment: a whiteboard in a cramped office, markers running dry. A student draws a simple axis, mass on one side, lifetime on the other, curving up steeply. She dots a point where the allowed PBH band sits. Her advisor draws a small flame at the low mass end and says, "Everything over here is already ash. Everything over there is stone cold." He taps the dot. These are the embers. And one more complication we can't dodge: the runaway finale. The last seconds aren't just hotter, they're faster. The mass loss rate spikes. The spectrum hardens. If a PBH dies within our cosmic neighborhood, it could write itself into our sky with a burst we'd see across observatories. We've listened for those Hawking pops. So far, silence. But silence is only a statement about now. This is the moment everything changes in how we think about time. With PBHs, the universe seeded clocks into its own fabric. We didn't wind them, but we live under their schedule. And their last breath might do more than light up detectors. Under the wrong conditions, it could nudge the vacuum itself. To understand why that finale is dangerous, we need the aftertaste of energy. We need to look at what a last exhale can trigger. The final second, runaway evaporation. It doesn't announce itself with a drum roll. The final second begins like any other second in the black hole's long life, hotter than a moment before, colder than a moment after. But the slope is different now. The mass is falling off a cliff. Temperature rockets. The quiet hiss hardens into a torrent. What used to be a gentle trickle of low-energy photons becomes a storm front of particles slamming outward from a shrinking horizon. Stakes first, because they're not abstract. End-stage evaporation concentrates unimaginable power into a volume that's vanishing. The smaller the hole, the tighter the focus. That means the energy density, the punch per cubic centimeter, spikes to levels the universe hasn't casually produced since its first fractions of a second. Space near the horizon becomes a furnace where quanta are born already sprinting. If one of these pops close enough, it could draw a line across our sky in high-energy light, a signature nobody could wave away. Action as it unfolded in the equations and the imaginations of people who trust them. As the temperature climbs, the spectrum hardens. First more energetic photons, then electrons and positrons arrive in force. Muons, taus, neutrinos, gluons. If the temperature clears the QCD scale, quarks and gluons spray out and immediately hadronize, fragmenting into jets of pions and other mesons that decay into gamma rays and neutrinos. It's not a single flash. It's a brief, chaotic shower where the whole acts like a collider with no engineering limits and no safety rails. The horizon shrinks between emissions, and with each tick the next emission is hotter and quicker. The cadence accelerates. Blink, flare, scream. Meanwhile, detectors wait. Ground-based gamma observatories stare at large patches of sky, looking for the telltale rise of a hard spectrum followed by a sudden cutoff. Space telescopes comb archival data for unassociated bursts that don't fit the usual gamma-ray burst families. A few claims have flirted with the idea, events that seem too short, too hard, too lonely, but nothing has survived the gauntlet of scrutiny. For now, there's only the expectation. When one goes, we'll know. Until then, silence. Complication hits right where the curve gets steep. Our math is semi-classical, and it's at its bravest when the hole is still large enough that spacetime looks smooth. In the last instance, the horizon shrinks to scales where quantum gravity shouldn't be a footnote anymore. Does a firewall form, tearing up the story we tell about smooth horizons? Do new channels open that bleed energy into hidden sectors? Does evaporation halt at a Planck mass relic, leaving behind a grain of gravity that never decays? Each option rewrites the finale. Each one changes what the sky would see. Human angle, a night shift at a high-altitude array. Air is thin, coffee is bad. A graduate student has a script running that flags subminute hardening events above a moving threshold. Every time it dings, her heart jumps. Mostly it's noise, cosmic rays pretending to be drama. She logs each false alarm anyway. The log is a small act of faith. Across the ocean, another team scrolls through years of data from a gamma satellite, training a classifier on known bursts to catch the misfits. They built a category called Hawking Pops. It's empty for now. Impact if one goes off nearby isn't subtle. A lunar mass black hole in its last breath would dump out a firework of particles and gamma rays that would light up wide-field instruments. Neutrino detectors might catch a whisper of the hadronic mess. If it happened within the solar neighborhood, amateur astronomers wouldn't see it with backyard telescopes, but the instruments meant for violence would. It would join the short list of signals that arrive with their own explanation baked in. But there's a switch hidden in that final instant, and it's the one people avoid naming because it turns the spectacle into a threat. High energy concentration in a small volume presses at the boundaries of our vacuum. If our vacuum is only metastable, good enough but not the best, the right kind of kick could, in principle, tip a patch into a lower energy state. In a kitchen, that's supercooled water snapping to ice when you tap the glass. In spacetime, That's a bubble of true vacuum forming and expanding at nearly light speed, rewriting physics as it goes. A PBH's last exhale, if it's hot enough and structured in the wrong way, could be that tap. Now nobody's claiming inevitability. Calculations put us uncomfortably close to the edge but not obviously over it. The Higgs potential hints, with caveats as big as galaxies. Still, the coincidence nags. End-stage temperatures in the rough ballpark, energy densities that don't happen anywhere else anymore, and a mechanism tied to horizons that couple interior and exterior states just when the fuse burns fastest. This remains firmly in theory space, plausible in models, unproven in nature. Meanwhile, even without catastrophe, the final second teaches us about horizons themselves. The information debate gets loud here. If evaporation is unitary, correlations among the outgoing quanta must crescendo at the end. That means the burst isn't random static, it's structured noise, with entanglement patterns we don't yet know how to read. The last breath could be the clearest broadcast a black hole ever sends, if anyone's listening with the right decoder. A micro-story to hold onto. A theorist sits on a balcony after midnight, laptop closed, city humming below. He's been calculating gray-body factors all day, the way the hole's curved space-time filters outgoing modes. He can't shake a simple image, a candle that burns for eons, then, in its final flicker, writes a message in smoke. Maybe it's nothing more than heat. Maybe it's the only note the universe still remembers how to sing from its childhood. We've listened for the note. So far, nothing. But instruments are sharpening, cadences are tightening. Archive searches get smarter. The final second hasn't visited our detectors yet, or if it has, we didn't recognize it. Either way, the fuse doesn't care. It burns. And if that last breath can do more than light the sky, if it can reach for the vacuum's hidden switch, then we need to talk about the vacuum we live in and why it might not be as safe as it feels. The vacuum that isn't guaranteed safe. There's a word physicists use when the floor looks solid but might not be: metastable. Good enough until it is. The stakes are simple and brutal. If our vacuum is only a temporary arrangement of fields and forces, then there exists a lower energy state, a truer vacuum waiting behind a barrier. Cross that barrier in one place and a bubble forms. The bubble doesn't drift. It sprints at near light speed, converting everything it touches to new rules. No alarm, no warning. Just a wave of different physics. Why do we even suspect this? The Higgs. When the Higgs boson showed up near 125 GeV and the top quark sat heavier than we hoped, a strange inference emerged from the math. Run the standard model backwards through energy scales and the Higgs potential. The energy landscape that tells the Higgs what value to sit at tilts ever so slightly the wrong way. Depending on inputs and how much faith you put in no new physics, our vacuum could be perched on a ledge. Not obviously doomed, not clearly safe, uncomfortably in between. Action the way the argument unfolds. You model the Higgs field's potential like a bowl with a little dimple. Our universe sits in the dimple, but there's a deeper basin far away across a barrier. Quantum mechanics allows tunneling. The field can, with unimaginably small probability, punch through and land in the deeper basin, nucleating a true vacuum bubble. The inside of that bubble has different constants and particle masses. Chemistry doesn't survive the border crossing. Neither do atoms. Neither do we. Complication 1. The numbers. In straight standard model calculations, the lifetime of our metastable vacuum dwarfs the age of the universe by absurd factors. On paper, we're fine. But that comfort comes with caveats. Add gravity corrections, high energy effects we haven't measured, or unknown heavy fields, and the tunneling rate can shift. Most shifts make us safer. Some don't. And here's where the PBH fuse intrudes. Concentrated energy can act like a seed. High-energy collisions, or a hot, tiny region driven out of equilibrium, can in principle catalyze a transition. A dying primordial black hole is very good at making hot, tiny regions. Human moment, small and honest. A physicist at her kitchen table stares at a napkin sketch of the Higgs potential: two valleys, a thin ridge. She says to her partner, "We'd never see it coming." She doesn't mean to scare anyone. She's just translating an equation into a feeling. If a bubble starts beyond our horizon, it's invisible until it's on top of us. If it starts locally, we don't get a headline. We just don't get. Meanwhile, calculations push both ways. Some argue black holes suppress false vacuum nucleation by warping spacetime, stretching the barrier, making tunneling harder. Others show that horizons can host instantaneous solutions, seeded bubbles perched near the edge that tip more easily. It depends on details, the exact Higgs top masses, higher dimensional operators, the temperature history, and whether evaporation couples to hidden sectors. The math is sharp, but the inputs blur. The result is a corridor of uncertainty, exactly where nobody wants a corridor. Impact isn't just existential, it's conceptual. If our vacuum is metastable, then the laws we recite are local customs. They hold because the field sits where it sits. A true vacuum bubble would rewrite the customs. New particle masses, altered couplings, different symmetry breaking. Gravity's behavior could shift. Inflation's fingerprints could be erased. Cosmology would reset without preserving anything that calls itself memory. On the other side, there'd be no we to compare notes. Link it back to the fuse we're tracking. A PBH's last second is a rare modern portal to early universe energy densities. The sizzling cocktail of quanta and fields in that shrinking volume could brush the Higgs field in precisely the wrong way. Not guaranteed, not even likely if you trust the safest versions of the calculation. But it's exactly the kind of spark that fits the mechanism. A local trigger in a world that otherwise only risks transitions through impossible diffuse chance. Here's the thing we keep avoiding. If a spark can flip the vacuum, who arranged the kindling? Why does the Higgs potential sit so close to the edge that we get to argue about it at all? Why do the surviving PBH masses align with energy scales tied to phase transitions in the early universe? It could be coincidence. It could be selection. We only live in vacua that support complexity, so of course we see one like this. Or it could be something with intent. We're careful with that word. Intent is a human label, but the pattern nags. The allowed PBH mass band brushes scales where sound speeds soften and density spikes during transitions. The Higgs potential's near-knife edge metastability makes our vacuum long-lived but not immortal. End-stage evaporation provides compact, energetic taps at random places and times. Add those up, and the cosmos looks like it's carrying both slow fuses and reliable matches scattered in the dark. Speculation stays in its lane, flagged, bounded by physics, not sold as fact. This is theory space, not consensus, but it reframes terror into something else. Design continuity, a plan you only glimpse when you line up the clocks with the landscape. If gardeners exist, they didn't leave letters. They left conditions. Seeds that compress information behind horizons. Fuses long enough to let complexity bloom. A vacuum that isn't absolutely safe, so restarts aren't impossible forever. It's a story you can't prove with one plot, but you can test piece by piece. To test any of it, we start with the vacuum we have. Keep pinning down the Higgs and top masses. Push for new physics or tighten the corners where it can hide. Model evaporation with more honesty near the end, include gravity's corrections, and ask how catalysis really behaves. And then, if a PBH pops and writes itself into our sky, we read it carefully, because buried in that burst could be the one detail that tells us whether the kindling was stacked on purpose. The Cosmic Gardener Hypothesis. This section is speculative. We're stepping outside consensus physics to ask a disciplined, what if, grounded in known mechanisms but not claiming evidence of intent. Intent changes how the story lands. Terror becomes design. What if the fuses and the kindling aren't accidents of messy physics, but the toolkit of a civilization that refused to let meaning die with one universe? Not letters in bottles, seeds in soil. In this story, the soil is space-time, and the seeds are primordial black holes placed where time can't easily rot them. Start with stakes. If intent sits behind PBHs, then the universe isn't just drifting toward a quiet fade or a sudden snap. It's participating in continuity. Continuity needs hardware that survives extremes and software that doesn't care about alphabets. It needs things that compress, preserve, And then, when the window opens, bias the next beginning. A message you can't burn, can't smear, can't forget even when you erase the chalkboard. Action sketched with what physics allows. A parent civilization, call them gardeners, faces the long tail of a cooling cosmos. Stars die, chemistry goes quiet, protons maybe survive, maybe don't. They need carriers that can last across eons, remain inert when it helps, and yet light up with structured dynamics when the moment comes. Black holes do both. Horizons protect structure, if information is preserved by unitarity, and evaporation eventually returns it, scrambled but in principle recoverable. Plant enough small black holes across halos, embed them in stable orbits, and you've salted the dark with release capsules. Why seeds, not messages? Entropy. Messages degrade, materials fail, languages drift. PBHs are the opposite of delicate. They're simple on the outside and potentially rich inside. If the end-stage radiation can carry correlations, the subtle patterns entanglement weaves, then those final bursts double as broadcast. Not a sentence in a human tongue. A bias in initial conditions, a nudge in symmetry breaking, a preference that steers how the next hot plasma cools and clumps. Robust, because even a tiny tilt can cascade, amplifying into galaxy-scale architecture. Complication. Can intent survive without intent-like signatures? The Gardner plan has to be time-proof. You can't count on your descendants reading your diary. You count on physics to read itself. That means engineering at the level of distributions, not devices. You choose masses that survive to the right epoch. You place seeds where gravitational potentials keep them safe yet visible to future observers. You aim for mass bands aligned to natural early universe scales, phase transitions, sound speed dips, so formation looks natural and selection effects can be blamed on cosmology, not construction. This remains speculative by design, an existence proof in theory space that we can probe with data. You build a story that can hide in the one kind of noise nobody questions, the universe's impact. If PBHs act as incubators, they can compress initial data behind horizons through accretion and interior dynamics, then later transmit that structure outward as the fuse nears its end. In a cyclic or bounce-like cosmology, concentrated late-time injections of high-energy quanta could seed features in a contracting phase or bias reheating after a bounce. In a one-and-done universe that's metastable, their deaths could seed vacuum transitions regionally, bootstrapping a child spacetime with slightly tuned parameters. Not magic, just exploiting how sensitive early conditions are when everything is hot and symmetric and close to the edge. We flag the speculation explicitly. This is theory space, not a claim of evidence. The bounds come from physics we do trust: Hawking radiation's mass, temperature relation, the lifetime curve, the evaporation spectrum hardening, the information story moving toward unitarity and page-time correlations. Layer on cosmology's rough edges, the Higgs potential hovering near metastability, PBH formation mechanisms that pick out mass scales, and you get a scaffold where agency could sit without breaking equations. There's a human moment here that's hard to dismiss. A theorist with a tidy desk and a ruthless allergy to fairy tales scribbles 3 words: design via distribution. Not a beacon that says hello, a histogram that nudges a phase transition. If someone wanted to talk across bangs, she says, they'd talk to the physics that all bangs share. She circles phase transitions and underlines horizons. Why would gardeners choose PBHs over, say, long-lived particles or relic crystals drifting in voids? Robustness and universality. Black holes don't care where they sit on the periodic table. They aren't brittle. They don't depend on a chemistry that might not exist next time. Their clocks are set by geometry, and geometry ages predictably. A seed mass of around lunar scale survives to late epochs but still dies on cosmological timescales, ensuring a signal arrives when a dying universe is quiet enough to hear it. Too heavy, and you get silence forever. Too light, and you flare before complexity can arise. The surviving mass window looks suspiciously like a designed sweet spot. Now the open loop that matters, patterns. If gardeners exist, their fingerprints won't be found on one object. They'll live in the statistics, mass banding near theory-pick scales, clustering that refuses pure Poisson, stratification in halos that mirrors a deployment plan rather than a random walk. And maybe, this is the long shot, subtle structure in burst ensembles from end-stage evaporation, correlations that fail simple randomness tests and hint at code riding on the tail of a spectrum. Complications stack up fast. Selection biases can fake structure. Instruments carve their own patterns into data. Any hint of mass quantization can evaporate under better calibration. Any claimed agency risks confirmation bias in a field that already loves stories. That's why the Gardner hypothesis doesn't ask for belief. It asks for tests we can falsify. Do the allowed PBH masses align with early universe energy scales more tightly than chance? Do microlensing durations cluster in bands predicted by a specific formation plus deployment model? Do gamma archives show burst ensembles with complexity lower than noise would allow? Impact, if even one signature survives the gauntlet, remains speculative. The universe would stop looking indifferent and start looking recursive. Not benevolent, not cruel, methodical. Continuity would become something we could measure, not just hope for. And if nothing passes, we still win because the search sharpens our models, cleans our data, and forces us to ask better questions about why our vacuum sits where it sits, and why the survivors in the dark prefer the masses they do. We're not selling comfort. We're sketching a possibility you can interrogate. Seeds, not sermons. Fuses, not threats. If the gardeners exist, they trusted physics more than culture. They buried their intentions in the one medium that lasts when stars and stories don't, gravity with a timer. Now the question is simple and brutal. If patterns exist, can we learn to see agency without inventing it? The next step is to hunt for patterns statistics can't fake. Patterns that shouldn't be random. This section is also speculative. We are outlining testable ideas, not asserting detections or intent. The goal is to design falsifiable checks for non-random structure. Start with the stakes. If intent exists, it won't announce itself with a neon sign. It'll hide where only patience can find it, in distributions, not anecdotes. Because physics is a statistics game, an agency, if it ever crossed a cosmic distance, would need to ride inside the one thing randomness can't perfectly mimic, structure repeated at scales that theory didn't require. Action begins in a room full of plots that look like weather. Event durations on one axis, sky position on another, weights for signal quality added like seasoning. The first test was simple. Do candidate PBH lenses land like raindrops, Poisson uncorrelated, or do they cluster in ways that suggest deployment rather than accident? Teams ran two-point correlation functions, computed Ripley's K, scrambled the catalogs to build nulls, then checked the real sky against the shuffle. No fireworks, but no clean shrug either. A low-level excess in some fields, gone in others. Enough to say, keep looking, not enough to say, we've found it. Meanwhile, mass hints crept in from microlensing durations. Translate a blink into a mass and you get a cloud of points. Someone traced a density ridge through that cloud and saw not a single ridge but bands, subtle plateaus where durations seemed to prefer hanging out. It wasn't dramatic. It was irritating. Because banding could be an instrument's heartbeat, a cadence alias, a pipeline artifact that makes noise look like rhythm. The team did what you do. Blinded reprocessing, independent pipelines, cross-checks with telescopes that don't share clocks. The bands softened, but they didn't vanish. Here's where theory walked back in. Early universe mechanisms pick scales. Inflation with a bump in the power spectrum seeds a characteristic mass. First-order phase transitions with softened sound speeds set a different one. Cosmic string cusps add yet another. If you overlay those predicted mass ranges on the fuzzy bands, something interesting happens. A few alignments look too neat to dismiss and too messy to claim. You get that feeling again, the dare, not the declaration. Human moment. A grad student working off hours because she can't let the pattern go builds a spreadsheet with every candidate event from 3 surveys. She color codes durations, then adds a column for the approximate horizon mass scale at QCD and electroweak transitions. On a lark, she bins by log mass and runs a simple periodicity test, not because she expects quantization, but because she wants the computer to prove her wrong. The spacing that comes back is weirdly close to what a phase transition ladder would give if the primordial spectrum had a modest tilt. She brings it to group meeting expecting an eye roll. Instead, her advisor says, "Let's try to break it." Complication hits fast. Selection bias is a liar with a good memory. The surveys catch what their cadences allow. If you sample night skies every few hours, you prefer durations of a few hours. If your detection threshold favors high-amplitude blinks, you nudge masses upward. Even the weather matters. Cloud cover carves structure into your catalog. To beat this, the team simulates the sky with and without PBHs, feeds both through the exact pipelines, and asks whether banding survives the abuse. In the synthetic universes with purely random compact objects, banding fades to statistical dust. In the universes seeded with PBHs formed at phase transition scales, low-contrast stripes reappear, fragile but traceable. Impact is measured in restraint, no press release, a preprint with caveats like guardrails. Suggestive, not evidence. The plot that lands hardest isn't the prettiest one. It's the one where instrument systematics are injected by hand and subtracted, leaving a faint residue that matches the energy scales we already argue about in the early universe. That residue doesn't prove intent. It does tighten the loop between observation and mechanism. Another angle, halo stratification. If seeds were planted, you might see radial preferences, more objects at certain galactocentric radii than smooth models predict. The team bins events by inferred distance along sightlines through the halo. The profile isn't obviously spiky, but there's a mild overabundance in a shell where tidal fields are stable and encounters rare. Dynamical models say that's where compact objects could survive longest without being disrupted. A gardener would have known that too. Parallel action across town. A different group tests mass quantization hints using a Kolmogorov-Smirnov approach on duration spacing. The null says spacing should follow an exponential if events are random in log mass. The data bends that curve just a little toward preferred gaps. It's barely there. They post the code and beg others to replicate or kill it. Replies trickle in. One replication in a different survey sees the same weak bend. Another finds nothing. The plot remains pinned to the corkboard labeled weird, but now it has friends. What nobody knew at the time was how the search would change the searchers. The grad student spreadsheet becomes a community benchmark. People download it, add their own columns, host galaxy environment flags, ecliptic latitude, seasonal cadence in an open attempt to prove themselves wrong. Over weeks, one artifact after another dies under scrutiny. A few features refuse to go. Impact isn't proof, it's momentum. Observatories adjust strategies. Faster cadence blocks to resolve sub-hour events, coordinated fields across hemispheres to cancel seasonal biases, simultaneous infrared vetoes to cull warm imposters. Gamma-ray teams build a burst ensemble program to test whether any cluster of unassociated hard events shares fingerprints, spectral tails, temporal microstructure, more alike than chance would allow. If end-stage evaporation carries structure, ensembles are where it hides. This is a testable hypothesis, not a conclusion. Caveat stamped in bold, evidence is suggestive, not decisive. A good statistician can make a ghost dance with the wrong prior. That's why the next steps are ruthless, blind injections, shared pipelines, cross-mission synchronization. The question is, are patterns pretty? It's can randomness plausibly fake all of them at once? Meanwhile, even if intent never enters, the lesson holds. PBH formation mechanisms alone can write banding into the sky. That's a brutal kind of meaning. The universe teaching us its thresholds by leaving pebbles at each one. Agency or not, the patterns point backward to to the forge that made the seeds, and forward to the fuses they carry. And that realization pushes us into the deeper trap of time, where black holes don't just weigh the dark, they edit the record of it. Time's one-way trap. While the pattern hunters chased bands and clusters, another realization crept in, colder than statistics. Black holes don't just weigh the dark, they curve the flow of time and tangle memory with geometry. If the universe ever felt like a book you could reread, black holes are where the pages get glued, torn, and, depending on who you ask, rewritten. Start with the stakes. If information can disappear into a horizon and never come back, then physics loses its grip on time's arrow. Because information lost isn't just a phrase, it's a fracture in unitarity, the rule that evolution is reversible in principle. Break that and you're not just misplacing details, you're admitting there's no path back. For a cosmos full of small horizons, the risk isn't academic, it's everywhere. Action. For years, the story went like this. A black hole forms, swallows what falls in, and radiates away like a perfect thermal body. Thermal means memoryless, so when the whole fades to nothing, the pattern of what fell in goes with it. Hawking's calculation said exactly that. Then came the pushback. If quantum mechanics is true everywhere, then evaporation must be unitary. The outgoing radiation can't be pure heat forever. Somewhere along the way, correlations have to show up. Enter Don Page and the Page curve. Entropy of the outgoing radiation rises at first, then, around the halfway mark, the Page time. It starts to fall as the radiation becomes more and more entangled with itself, quietly encoding the inside story. Meanwhile, holography rewired the problem. If gravity in a volume can be described by a theory living on its boundary, then horizons aren't dumpsters, they're ledgers. The AD-SCFT correspondence wasn't our universe, but it was close enough to prove a point. Unitary evaporation is possible in a quantum gravity world. Later, island calculations made the Page curve concrete in models, include quantum extremal surfaces, and the entropy turns over right on schedule. Translation for the rest of us. What looked like shredded memory might be recoverable in principle if you know how to read the correlations. Complication. Principle isn't practice. A PBH with a lunar mass crosses its Page time long before a supermassive hole does. Smaller horizons hand off their secrets earlier. Their hiss stops being innocent noise and starts carrying long strings of entanglement. But the decoder isn't something you bolt to a telescope. You need global access to the entire radiation field, perfect control, and a patience measured in cosmic calendar pages. That gap between in principle and in practice is the trap. The universe can obey unitarity while behaving on every useful timescale like a machine with auto-delete. Human moment. In a seminar, a young theorist draws two curves, one that climbs forever, another that climbs and then dips. This, she says, tapping the dipping one, is the Page curve. It says the universe doesn't forget, but it also says you can't ask for your answer back early. A hand goes up. So, for small PBHs, she nods. They start giving back meaning sooner, but you still have to catch it. Impact lands here. If the dark is studded with small horizons, ours is a cosmos with everywhere local shredders of history that only reluctantly reassemble the shredded strips at the end. Every 30 seconds, ask why we should care. Because time's arrow isn't just about entropy going up. It's about what it means to recover a past. If the necessary correlations are spread thin across light years of faint radiation, then for all practical purposes, the past is gone. Not erased, smeared beyond retrieval. Meanwhile, there's a deeper twist. Black holes are fast scramblers. Toss in a diary, and its information mixes with the hole's degrees of freedom in a time set by its temperature and size, astonishingly quickly by cosmic standards. When radiation starts returning information, it's not a sentence, it's 1,000 crosswords, each solvable only if you have all the others. Small PBHs hit their scrambling and Page milestones early, so their late-time emissions are where the puzzle pieces finally fit. That's the fuse again, but now it's a timeline for memory. Complication erupts in the firewall debates. If late-time radiation is entangled with early-time radiation to preserve unitarity, then it can't also be entangled with interior modes at the horizon without breaking quantum monogamy. Something has to give. Smooth horizons, effective field theory, or the purity of the outside state. People argued that a firewall, a burst of high-energy drama at the edge, must form to cut the interior ties. Others built ways around it with state dependence, equals Epper bridges or islands. The math evolves. The question remains, what does a late-stage PBH horizon feel like to the quanta it emits? Another human moment. A blackboard full of entanglement wedges. Someone sighs. We're trying to save 3 good ideas and only 2 can survive unchanged. They erase half the board and keep the part that predicts a page curve we might someday infer indirectly, from the distribution of burst microstructures, from the way ensembles deviate from perfect thermality. Impact zoomed out. The universe behaves like a memory machine with a delayed refund policy. Small PBHs tick through their promises faster, but the payout arrives as whispers, not declarations. That's why the stakes from earlier chapters bend inward here. If end-stage evaporation can carry structured correlations, and if, as the Gardner hypothesis suggests, anyone intended to ride those correlations, then time's trap becomes a channel. Slow, lossy, cruel to the impatient, but a channel. Link back to the fuse and forward to the powder. Each PBH is a timer and a shredder, and the moment its radiation stops looking like heat and starts looking like code is when it can influence more than its surroundings. That's where the human need to build meaning meets the physics of horizons. We've been looking for patterns in masses and positions. Soon we'll look for patterns in time itself, how information trickles when it surges, whether late bursts share a grammar. To get there, we accept the trap without surrendering to it. We build surveys that stack faint signals, we design tests that sniff out correlations across events, and we rethink what evidence looks like when the message is smeared across the sky. Because the next step is violent and precise. The forge that made the seeds and the thresholds that stamped their scales are where fuse meets powder. 3 chapters back we circled those scales. Now we walk into the early universe violence that minted the seeds and maybe wrote the first lines of a message we're only now learning how to read. Where seeds are forged, early universe violence. To see where the seeds came from, we have to walk back into a time when the universe was too young to remember itself. Not stars, not atoms, just a hot fluid of fields and radiation, expanding, cooling, and thundering with quantum noise. In that chaos, density didn't spread evenly. It bunched. And when a patch bunched past a threshold, gravity didn't wait for chemistry. It collapsed. Stakes first. PBHs don't form just anywhere. They need a moment when the pressure support of the early plasma can't push back fast enough. There's a critical overdensity, go above it, and a region inside the cosmic horizon stops being part of the expanding flow and becomes a self-contained fall. That threshold is the gate. Not many regions cross it. The ones that do can define epochs. Action starts with inflation's fingerprints. Inflation, an almost absurdly rapid expansion, smooths the universe and seeds it with tiny quantum fluctuations. Mostly, those are small, the kind that grow into galaxies over billions of years. But if the inflattened field's potential has a bump, an inflection where its roll slows and amplifies certain wavelengths, then the power spectrum spikes on a narrow band of scales. When those scales re-enter the horizon later, the overdensities can exceed the collapse threshold. Translation: a pause in the early roll can plant a row of seeds. Meanwhile, phase transitions add their own violence. As the universe cools, symmetries break. The QCD epoch, when quarks bind into protons and neutrons, softens the equation of state. Pressure responds less stiffly to compression. That softening lowers the bar for collapse. A modest overdensity that would have bounced at higher sound speeds can now tip over. If you form PBHs here, their masses reflect the horizon mass at that temperature. That's one origin for the banding from earlier. Horizons at phase transitions have specific sizes, so the PBHs they mint prefer specific masses. Complication: you don't just get one mechanism. Cosmic strings, if they exist, drag long tension lines across spacetime. When a loop forms and a cusp snaps, energy concentrates violently. Under the right conditions, those cusps can collapse into black holes, again with masses tied to the loop scale at that era. Add all this up and the early universe looks like a workshop with multiple tools, some carving broad distributions, some stamping narrow badges. What nobody knew at the time is how sharp the threshold is. Collapse isn't a gentle slide, it's a cliff. The probability of making a PBH depends exponentially on how close the fluctuation amplitude is to the critical value. That makes formation rare, vanishingly so, unless a mechanism nudges the distribution. That's why a small, well-placed enhancement in power during inflation can matter more than 100 noisy background bumps. It's also why the survivors are precious. The universe wasn't making these by the trillion, it was sneaking them in. Human moment. A theorist draws a horizon mass curve against temperature. At higher temperatures, the horizon holds less mass. As the universe cools, the horizon mass climbs. She shades a band near the QCD transition and writes lunarish in the margin. A student leans in. That's where our microlensing durations land. The room goes quiet in a way equations can't fake. Impact ripples through the models. If the microlensing candidates pile near lunar mass, inflation bumps that target horizon or QCD softened collapse becomes the cleanest path. A different team, working the heavier end, shows how an inflationary spike on larger scales could feed the LIGO era binaries. Two bands, two mechanisms, same story. Early universe violence choosing scales. Meanwhile, each mechanism leaves a signature beyond mass. An inflationary spike produces PBHs distributed like the underlying Gaussian field, closer to Poisson. Phase transitions can correlate seeds with regions of delayed reheating or sound speed dips, biasing clustering. String cusp collapses might carry anisotropies tied to network geometry. Those aren't trivial to extract from today's sky, but they're not hopeless either. Lensing maps, dynamical heating of small galaxies, and stochastic gravitational wave backgrounds all respond differently to different PBH spatial patterns. Complication arrives with constraints. The same spikes in power that help seeds form also produce second-order gravitational waves when those fluctuations re-enter the horizon. Those waves add up into a background today. Pulsar timing arrays and in the future space-based interferometers can hear that background. If they don't, the spike can't be too high, but the window isn't slammed shut. You can thread it with a spike narrow enough to dodge current ears and loud enough to tip a few patches over the threshold. Another micro story. A postdoc runs a Monte Carlo of universes where the inflaton lingers over a shallow inflection for an extra whisper of E-folds. In most runs, no PBHs. In a sliver, it rains just enough seeds to matter. He prints the histograms, tapes them next to the lensing duration plot, and just looks. He isn't claiming truth. He's checking if the shapes rhyme. Impact, again, is about alignment. The same scales that look forbidden in lensing, too many short-duration events in certain fields, line up with the horizon masses at plausible transitional physics. It isn't neat. It's noisy, blurred by selection, smeared by dynamics. But there's a through line you can't unsee once you've seen it. The forge tunes the seed sizes, and today's whispers still remember. Open loop. The forge might have done more than mint seeds. If late-time evaporation couples interior states to outgoing quanta, then the interior could have recorded a trace of the forge, how the fluctuation crossed the line, what the local field values were. If those traces influence the late burst, then end-stage events don't just shout, "I'm dying." They hint at here's how I was born. That's a long shot, but it's the right kind, testable in ensembles, falsifiable with better models. Transition is simple. To follow that hint, you have to watch the messenger at the boundary, the horizon. Not a wall, a switchboard. We've talked about clocks and fuses. Now we watch how horizons route energy and information, and ask whether the final bursts can carry anything but heat. Horizons as switchboards. We've been treating horizons like borders. This side, that side, nothing crosses. That's useful, but it hides what they really do. A horizon is a processing layer. It routes energy and scrambles information so fast that what goes in and what comes out aren't independent. They're linked through the most efficient mixer nature ever built. Start with stakes. If the horizon is a switchboard, then end-stage evaporation isn't random heat. It's rooted output shaped by the interior state and the geometry at the edge. That means a dying PBH might broadcast structured noise, patterns subtle enough to dodge most searches, strong enough to matter in ensembles. If there's any structure to read, the horizon is where the message gets formatted. Action begins with the membrane paradigm. It's a trick that rephrases the mathematics. Treat the horizon like a physical surface with viscosity, conductivity, and charge. Not because it's literally a membrane, but because to outside observers it behaves that way. Fields that fall in induce currents and stresses on this fictitious surface, and those in turn determine the outgoing response. Translation. The horizon acts like an interface device, encoding interior influences into the radiation we can see. Meanwhile, black holes are fast scramblers. Toss in a qubit, wait a scrambling time, and its information spreads across the horizon's degrees of freedom like ink in water, only faster than any ordinary system can manage. When Hawking radiation starts returning information after the page time, the horizon scrambler has already mixed the interior diary into a collective state. The switchboard doesn't pass through pages, it routes correlations. Complication arrives with the firewall debates. If late-time quanta must be entangled with early radiation to keep evaporation unitary, they can't also be perfectly entangled with interior partners just inside the horizon. One fix slices the smoothness at the edge. Another bends our notion of locality with wormhole-like equals EPR connections linking the inside to the outside radiation. Either way, the horizon's job description changes. It's not a mute barrier. It's an active router that trades naive locality for global bookkeeping. Now add the recent island story. When you compute the entropy of Hawking radiation carefully, quantum extremal surfaces, the islands, tell you to include parts of the black hole interior as if they belong to the radiation's description. That sounds abstract, but it means this. The correct description of the exterior includes an encoded shadow of the interior. A switchboard again, this time with the wiring diagram written in entanglement geometry. Human moment. A skeptic stands at a whiteboard, arms crossed, staring at a sketch of a horizon covered in little arrows ingoing, outgoing, tangling across the surface. One equation, just a neat relation between scrambling time and temperature, lands heavier than the rest. She squints, rubs it out, redraws it, then steps back and says quietly, "So the only way this makes sense is if the surface already knows the inside." She doesn't like the sentence. She likes the math. Meanwhile, the late-stage coupling matters most for us. As the hole shrinks, gray-body factors, the way curvature filters outgoing modes, shift, favoring higher energies and different angular patterns. Those filters aren't arbitrary. They depend on horizon geometry and interior content through how the switchboard routes modes. If the interior microstate retains any imprint of how the PBH formed, say, the shape of the overdensity that collapsed or the field configuration during a phase transition, then some faint, repeatable features could survive in the late bursts time, energy microstructure. Impact is immediate in how we propose to listen. Instead of chasing single smoking gun flashes, we build catalogs of short, hard bursts with precise time tagging and energy binning. Then we cross-correlate across events. If the switchboard imprints a shared grammar, tiny spectral wiggles, preferred interphoton intervals, characteristic polarization rotations, we won't see it in one burst. We'll see it only when stacks of bursts refuse to average to perfect thermality. Complication. Nature loves to fake structure. Instrumental dead time, pileup, atmospheric absorption, detector gain drifts. Each carves fingerprints that look like patterns. So the tests have to be ruthless. Multi-instrument coincidence, Earth occultation controls, time-scrambling nulls, and synthetic skies push through pipelines until fake grammars bleed out. Only then do we ask whether any residue stays put across detectors that don't share sins. Parallel action in theory. People compute out-of-time-ordered correlators, measures of scrambling, to predict what late-time two-point and higher-point functions should look like if the horizon is a fast mixer encoding interior data. The predictions are, you'll see Morse code at 300 kV. They're constraints on how far from thermal the spectrum can tilt and still satisfy unitarity with islands. The practical takeaway: look for specific deviations in cumulants of the photon count distribution across energy bands and microsecond windows. Human microstory. A postdoc stares at a screen of simulated bursts, rows of jagged lines that all look like weather. He flips the view to a weird space, principal components of the time-energy covariance. Most bursts smear into a fuzzy cloud, a subset clumps. He frowns, reruns the whole thing with different random seeds, injects detector artifacts by hand, subtracts them, and the clump weakens but doesn't die. He doesn't call it structure, he calls his advisor. Impact, if even a weak, repeatable grammar survives the gauntlet, is more than a curiosity. It says the switchboard routes interior history into the sky in ways we can measure. It validates the idea that late evaporation is a broadcast channel, not just a heater. And it closes a loop. If PBHs formed at specific early universe thresholds, and if horizons keep even a whisper of that birth certificate, then end-stage bursts are where the forge writes back. Of course, we could find nothing. The horizon could be the ultimate shredder, unitary in principle, hopeless in practice, with deviations from thermality too tiny for any real instrument. That result would still teach us something, that the switchboard's wiring hides deeper than we can reach, that if there's a message, it chose a code beyond our patience. But the hunt clarifies the question we're really asking. Because if horizons are switchboards, then it's reasonable to ask whether anyone ever tried to use them intentionally. Structure suggests messages. Messages imply senders. We don't leap to that conclusion. We test for it. And the next step is to lay out how a dying PBH could carry blueprints, not words but biases, that tip the next hot beginning. That's where we go next. Could PBHs carry blueprints? If horizons are switchboards, then the question stops being, do they broadcast? And becomes, what could ride on the broadcast? Not sentences. Not symbols we drew on cave walls. Blueprints in the only language the next beginning is guaranteed to speak. Correlations that bias physics when it resets. Start with the stakes. If dying primordial black holes can carry structured correlations in their final radiation, then their last breaths can do work. Not engineering in the usual sense, but a gentle shove on the initial conditions of whatever comes next. How fields settle, which symmetries break, how matter clumps. Even a slight bias can avalanche in a hot, unstable plasma. That's enough to put fingerprints on a new sky. Action starts with how a code could exist without an alphabet. After the page time, the radiation isn't featureless heat. It carries entanglement structure tied to the black hole's microstate. If that microstate remembers anything about formation, phase transition environment, local field values, shape of the collapse, then those memories can leak as higher-order correlations among outgoing quanta. You won't hear hello. You'll measure that photons in band A covary with photons in band B on microsecond scales more than randomness allows, and that the same covariance pattern recurs across multiple bursts. Meanwhile, you sketch how such patterns could matter for a restart. In bounce and cyclic cosmologies, late-time, high-energy injections feed into the contracting phase's stress-energy budget. They seed in homogeneities that, after the bounce, remap into density variations. If the burst ensemble shares a grammar, correlation matrices that prefer certain scales, those scales can reappear as slight tilts in the primordial power spectrum after reheating. In one-shot vacuum decay stories, a catalyzed bubble inherits field fluctuations at the nucleation site. Structured energy dumping can nudge the bubble wall's initial geometry, biasing the spectrum of excitations it spawns as it thermalizes. It's not a lever, it's a nudge, precisely the sort of nudge that early universe physics magnifies. Complication. Noise is a bully. Individual bursts are sparse, messy, filtered by gray-body factors and instrument response. So the code can't live in any one event. You need an ensemble. That's why the search idea shifts from catch the pop to characterize the population. You stack bursts, build time, energy co-spectra, compute multi-point cumulants, and compare them to thermal surrogates and to models of late evaporation that include islands and scrambling. If a low-dimensional structure pops out, say, repeated eigenmodes in the covariance that line up across events, you've found grammar. Human moment. A small group huddles around a monitor displaying a forest of lines, principal components ranked by explained variance. The first mode is boring, overall hardness. The second is uglier, an oscillation in the 100-300 key V-band that recurs more than chance would like. A junior researcher asks, could that be detector dead time? The instrument lead shrugs. Maybe. Let's break it. They inject fake dead time, retrain the decomposition, and watch the oscillation shift but not die. Not a code. Not yet. But not nothing. Impact, if even a weak grammar survives, is multiplier math. A tiny bias in symmetry breaking. 1 in 1,000 more domains choosing a particular vacuum orientation can, after percolation and reheating, yield percent-level differences in density variance at certain scales. That cascades into the statistics of early star formation and halo assembly, producing subtle preferences in galaxy orientations, void sizes, and lensing shear correlations. We're not there yet, but that's the pipeline. Burst grammar to initial bias to sky texture. Complication 2, Kolmogorov complexity. How do you prove a pattern is code and not a fluke? You don't in one stroke. You measure the algorithmic complexity of burst sequences and compare it to surrogates with identical spectra but scrambled phases. If real bursts are systematically simpler, compressible in the same basis, beyond what thermal physics predicts, that's evidence of structure. You repeat across instruments, seasons, and sky regions. You publish the negative results with the same zeal. Meanwhile, you design tests the next decade can actually run. Gamma observatories adopt microsecond time tagging and cross-calibration standards, so stacked analyses don't drown in clock drift. Neutrino detectors flag subminute upticks coordinated with hard gamma spikes to isolate hadronic cascades. Radio arrays monitor for coherent afterglows. Brief, band-limited chirps that some models predict when charged showers traverse plasma near the dying hole. You also mine archives. Short, hard, unassociated bursts that past missions discarded because they looked like glitches. If a subset shares the same low-rank covariant structure, you have a lead. Human microstory. In an office lit by a single desk lamp, a grad student writes a line on a sticky note. Code isn't content, it's constraint. She pins it above her screen. It changes how she works. Instead of hunting for messages, she hunts for limits on randomness that repeat across events. Her first 3 papers are nulls. The 4th finds a stubborn, instrument-agnostic dip in complexity at a specific timescale. She doesn't call it a blueprint. She calls it a bound we can't explain yet. Caveat stamped clearly. This is theory-forward and evidence-limited. The Gardner angle isn't required. Even without intent, structured correlations could ride late-time radiation because unitarity demands them. The claim we can test soon is modest. Do ensembles of short, hard bursts cluster in complexity space more tightly than thermal surrogates? Do those clusters line up with PBH mass bands inferred from microlensing statistics? If yes, agency stays a hypothesis. If no, we've still learned where the switchboard hides its wiring. Impact, either way, is a new kind of listening. We stop waiting for a single spectacular pop and start building a census of microstructures. We treat horizons like transmitters we didn't build, and we accept that the only blueprints they'll ever carry are biases, Small, stubborn tilts in how energy leaves and how the next universe might begin to arrange itself. That's not poetry. It's a plan you can falsify. And speaking of plans, someone has to look. Not someday now. The hunt needs cadence, coincidence, and discipline. Who's actually watching the fuse, and how would we catch a seed in the wild? That's where we go next. The hunt, how we'd catch a seed. If seeds exist, we need a way to net one without fooling ourselves. Stakes first. Find one, confirm it's not a rogue planet, not a brown dwarf, not a software ghost. Then clock its life, mass, motion, environment, and build a case that it's a black hole too small to shine and too stubborn to be anything else. Action starts where the whisper began, microlensing. You stare at a crowded star field and wait for a star to brighten and fade as a compact lens wanders by. Duration scales with the square root of mass and the lens's speed. For lunar mass candidates, you're talking hours to a day, blink and it's gone events that standard cadence surveys routinely miss. So teams retool, faster cadence blocks, overlapping exposures, rolling shutters that trade depth for time resolution. They pick sightlines through the galactic bulge and Magellanic clouds, where star counts are high and relative velocities favor short, sharp lenses. Meanwhile, you add the first filter against imposters, infrared veto. Free-floating planets glow, however faintly. Brown dwarfs are dim but warm. A primordial black hole has no photosphere, so you co-observe in near-infrared and optical. If the lensing curve is clean and there's no infrared counterpart down to brutal limits, the candidate gets a green check, not a trophy. You also check proper motion. Ejected planets carry the dynamical scars of their eviction, motions that don't match halo kinematics. PBHs should prefer halo-like velocities and isotropic directions. Stack enough events and their motions tell you which population you're seeing. Complication. Instrument ghosts masquerade as drama. Pixel defects, cosmic ray hits, atmospheric scintillation can fake short bumps. The antidote is coincidence. Two telescopes, separated by hundreds of kilometers, watching the same field see the same microlensing curve, time-shifted by Earth's parallax. Triple it with a space-based vantage point, say, a small-set rideshare that stares at the same stars, and you get an unforgeable geometric signature. 3 curves with precise time offsets traceable to a single moving lens. Now your event isn't just pretty, it's triangulated. Impact, once you lock a handful, is leverage. With parallax you estimate distance, with duration you estimate mass, with non-detection in infrared you rule out warmth. Combine all 3 and your candidate climbs the ladder from weird to compelling. A small group assembles a short list and names it what it is, a target catalog for multi-messenger shadowing. Parallel action shifts the hunt to the background hum, gravitational waves. Not the thumps LIGO hears from stellar mass binaries, but a murmur from countless tiny mergers and inspirals if PBHs cluster. Pulsar timing arrays already reported a low frequency, background likely from supermassive binaries. Push to higher frequencies with next-generation detectors, and you can begin to carve out limits, or hints, of compact object swarms. Space-based interferometers like LISA open a window where subsolar mass binaries might sing. Even a single detection of a subsolar mass merger would be a flare in the sky spelling primordial, because nature struggles to make such small black holes in stars. While that's gestating, a more immediate game runs on the limb of the moon. Lunar occultations, stars winking as the moon's edge slides by, offer a sharp knife to cut timing. If a compact lens sits near the line of sight during an occultation, the diffraction pattern carries a telltale distortion. Fast photometers on small telescopes can scan thousands of stars per night along the lunar limb. Weird, yes. Cheap, also yes. A handful of teams quietly tune their pipelines to flag the odd fringes that a lunar mass lens would sculpt. The near-term stakes get louder when you talk about deaths. If the allowed mass band truly spills to the low end, a few PBHs could be in their late loud phase within the Milky Way neighborhood. Gamma ray observatories, Fermi, HESS, MAGIC, VERITAS, already sift the sky for hard, subminute bursts. The hunt pivots from single-event spectacle to an ensemble program, microsecond time tagging, standardized energy binning, and immediate cross-facility alerts when a hard spectrum with a rising temperature and sharp cutoff appears. Neutrino detectors listen in coincidence for hadronic whispers. Radio arrays schedule fast response blocks to sniff for coherent afterglows predicted by some models. Archive mining becomes a sport. Unassociated spikes dismissed as glitches get a second trial with new criteria aimed at hawking endgames. Human moment. A night operator at a small Chilean telescope watches a field the big surveys ignore. An alert pings, a 2-hour symmetric rise and fall with a clean baseline. She checks the parallel feed from a sister telescope in South Africa, same curve, time-shifted. The infrared camera shows nothing where a planet should smolder. She marks the candidate and writes one sentence in the log. If it's a rock, it's a very cold rock. Then a sharper line for viewers. Gravity doesn't glow. Complication that keeps everyone honest. False positives scale with ambition. Free-floating planets can be colder than you think. Binary stars can mimic symmetry. Pipelines learn your expectations and feed them back to you. So the criteria tight. Require parallax, demand infrared non-detections to deeper limits, cross-check velocities against halo priors, and where possible, revisit the same fields months later to measure residual proper motion. A real PBH leaves no trace but gravity. Everything else leaves some hint of itself. Impact isn't a press conference. It's a threshold crossed quietly when the third or fourth event with all the right boxes ticked lands in the catalog. Conferences reserve time for compact dark candidates because the stack of maybes starts to look like a slice of yes. Particle detectors don't power down. They pivot to models that let PBHs share the stage with light relics. Theorists prune their forests of mass functions against the new constraints. Observatories lock in cadence blocks for the long haul because seeds don't care about grant cycles. And a last stake, ethics. If you can predict that a nearby seed is small enough to die in, say, 1,000,000 years, you haven't found a doomsday clock for humans. You've found a responsibility. What we publish, how we frame it, and when we ring bells will shape trust. The fuse burns either way. The hunt's job is to make sure we see it, not to scare, not to soothe, to know. The ethical bomb. We've been chasing seeds and fuses. Now we hit the part that doesn't fit neatly on a whiteboard. What to do with knowledge that can scare the daylight out of people and still be true. The stakes are simple and ugly. Public panic helps no one. Apathy helps even less. Somewhere between we're doomed and nothing to see is a path that keeps trust intact while science does its job. Action starts with a memory. When particle colliders switched on, a handful of papers asked whether high-energy collisions could make black holes that eat the Earth. The math said no by laughable margins. Still, committees wrote risk assessments anyway because the public asked. When gene drives arrived, biologists paused, convened, and drafted governance before releasing anything into a field. Geoengineering, endless workshops, frameworks, caution, and footnotes. In every case, the science moved forward. In every case, the conversation mattered. Complication. You can't turn off the universe. There's no red button for vacuum decay, no pause key for a dying PBH 100 light-years away. That leaves only narratives. If the hunt finds a handful of clean PBH candidates, and if gamma instruments start to see a family of short, hard bursts with the right microstructure, do you post the preprint on a Friday and call it a week? Or do you sit on it until you've strangled every artifact? If you wait, you risk eroding trust when the leak comes from somewhere else. If you rush, you risk shouting fire with a stack of maybes. Human moment. A late-night email thread in a department that usually argues about grant deadlines. Subject line, candidate for press or preprint. One reply says, publish fast with caveats, the data won't get cleaner sitting in our drives. Another says, hold, re-reduce with a third pipeline, then bring in an external team to audit. The chair writes, compromise, embargoed briefing to observatories, and a public preprint with a plain language appendix. We own the uncertainty. Meanwhile, there's the governance that isn't written yet. Who coordinates when a burst hits the Hawking Pop classifier with high confidence? Astronomers know how to share supernovae, gamma bursts, kilonovae. There are VO event streams, public alerts, community norms. This is different only in how people will read it. So the fix is boring and necessary. Extend the alert protocols with agreed language bands, candidate, probable, high confidence, and attach required context, distance limits, energy estimates, and the explicit statement that this has nothing to do with imminent danger to Earth. Template the words before you need them. Impact policy follows language. If the first public story readers see is micro black holes are about to blow up, you've already lost. If the first story says, we've found compact dark objects that bend starlight, they may be ancient black holes evaporating at imperceptible rates. The end stage, if it occurs within our galaxy, would be brilliant in telescopes and harmless in backyards. You buy space to think. The truth doesn't soften under good phrasing, it lands. Complication 2 cuts the other way. Over-sanitizing breeds suspicion. People can smell varnish. So the rule is candor with calibration. Say what you know, what you don't, and how you'll know next. Put the constraints in human terms without turning them into cartoons. Translate lunar mass PBH lifetime into a number that means something, longer than the age of cities, shorter than the age of galaxies. Then resist the urge to promise certainty you don't have. Another human moment. A science communicator drafts a video script. First version leans on dread, second on comfort. Neither fits. The third keeps the fuse, keeps the math, and swaps threat for responsibility. She records it with a line she won't cut. Curiosity is not a crime. Hiding is. Comments still fill with doom, but a lot of them ask the right questions. Meanwhile, open data isn't optional. If you want the world to trust that you didn't conjure patterns from noise, you publish code, calibration files, and null tests. You invite adversarial replications. You set bounties for breaking your claim, not because you like pain, but because transparency is the only antidote to conspiracy when the topic is, the universe might carry a fuse. The fastest way to diffuse bad narratives is to let 10 smart strangers try to tear yours apart. Impact on the inside of science is just as sharp. Graduate students deserve guardrails. If your lab is working a high-visibility candidate, you set norms. No screenshots on social, no numbers without uncertainty bars, no leaks to friends. You also make space for dissent. The person whose job is to say, this could be a planet, is your best defense against later embarrassment. Reward that person publicly when they kill a pet result. Complication 3 is money. Headlines invite donors and opportunists. If the phrase primordial black hole starts trending, proposals sprout like weeds. Agencies get nervous. The fix is slow and dull. Insist on peer review, long-time baselines, and funding lines that don't evaporate when the news cycle moves on. This search outlives election calendars. There's a final ethical edge, hope. If the Gardner hypothesis wanders into public view, and it will, people will project meaning onto it. Some will find comfort, some will build faiths, some will see malice. You can't referee belief, but you can keep the boundary bright. Mark speculation as speculation. Say could where you mean it. And remind everyone that the tests are the point. If the patterns wash out, we learn something grand about the early universe anyway. We end with a simple choice. We can clamp down, go quiet, and let rumor fill the silence. Or we can narrate the uncertainty in real time, shoulder the risk of being wrong in public, and keep the trust we'll need if the fuse turns out to be real. The universe denies us control. It still leaves us agency in how we speak, how we share, and how we carry news that might outlast us. The next big bang is personal. Meaning survives as structure. We can choose what persists. Open data, shared methods, resilient archives, teaching curiosity like a craft. Legacy isn't bodies, it's patterns handed forward, math, music, maps, hitched to physics that outlives us. Seeds grow where we tend them. If the fuse is real, responsibility beats fear. We can still aim the ending. Subscribe for the follow-up on the PBH search and watch our episode on Vacuum Decay, the missing piece that makes this puzzle click. One line to carry with you. The fuse is burning, but we choose what we light.